Okay, thanks so much. All right, so my name is Nate Tenpas. I'm a student of Doug Hardin and Ed Saff at Vanderbilt. And yeah, I'm going to be talking about some optimal sets of periodic point configurations and optimal in a sense, which we'll describe here. This is all going to be ongoing work, or ongoing work with Doug over the last year or so. So let's begin by just setting up some notation for the discrete energy minimization problem. Hopefully we've seen before. So take a compact set X and a kernel K, which is defined from X cross X into the extended reals. Our kernel should be lower semi-continuous and symmetric. Then for any multi-set omega sub n, which is contained in the set X, we can define its K energy to be summing up K at all the distinct pairs Xi, Xj of the multi-set, excluding the diagonal. And then we're interested in minimizing this energy. So we'll define the minimal discrete endpoint K energy of the set X to be script E sub K of Xn. And that's the infimum over all multi-sets of cardinality n contained in X of the energy. By the semi-continuity and compactness assumptions, we're guaranteed to get some configuration, which is actually achieving this infimum. And if configuration omega n achieves the infimum, we'll call it K optimal. So the next few slides then are devoted to setting up what energy problem Doug and I are interested in. So what is the compact set X, and what is the function, or what is the kernel K that we're working with? So take lambda to be a full rank lattice in RD. If you've got a nice function of rapid decay, say a Schwartz class function or a Riesz potential with the decay fast enough greater than the dimension of the space, then we can periodize that function by the lattice lambda. So how do we do so? We just sum up the function little f at all lattice translates, and the rapid decay is going to ensure that this function big F, the resulting lambda periodization, is well defined and has nice properties if little f does. So one such example is the classical one-dimensional theta function, where we take a Gaussian and we periodize by the integer lattice. We'll get this sum here on the right and up to a constant multiple, this pi over c square root of c over pi. That's the classical one-dimensional theta function that shows up in lots of number theory applications, and this will be important for us later. So our kernel is ultimately going to be a lattice periodization of some nice function f, little f. Okay, now what's the set X? Well, if we take this lattice lambda to be generated by vectors v1 through vd, it has this canonical fundamental domain, which is all the linear combinations of v1 and vd, where the coefficients are chosen between 0 and 1. And so that's going to be the compact set in which these multi-sets live, compact in the sense of the flat torus topology. Okay, so we're studying the energy problem where X, the compact set, is this canonical fundamental domain. And then our kernel is given by the lambda periodization of some function little f. And if we start with a nice function, say we start with a Schwartz class function, we're going to end up with a function in L2 of the canonical fundamental domain. But this is still a really broad class of kernels. And so we should restrict to a narrow class of little f, a narrow class of things which will periodize, so that we can hope to get general results about the minimizing configurations. So let's restrict to functions little f, which are rapidly decaying, to ensure that the lattice periodization makes sense, and also completely monotone functions of distance squared. And if you haven't seen it, completely monotone means the function or the derivatives of the function are alternating signs. So the function is non-negative, the derivative is non-positive, the second derivative is non-negative, and so on and so forth. This class is going to have a lot of the functions we care about, namely it has the Riesz potentials, and it also has these Gaussians as well. And these Gaussians are a particularly important example because in some sense they characterize the class. So by a theorem of Bernstein, an old theorem of Bernstein, the following two conditions are equivalent on a multiset omega n. So the first condition is that omega sub n, it's optimal for every lattice periodization where we periodized a function of rapid decay, which is completely monotone of distance squared. And then there's this seemingly weaker condition that omega sub n is optimal for only those lattice periodizations of Gaussians. And it turns out that these two are equivalent. If you are optimal for the Gaussians, you're optimal for all the periodizations, if you're optimal for periodizations of the Gaussian, you're optimal for all periodizations of completely monotone functions of distance squared. And that's a really nice property for a multiset to have. So if we have a multiset of cardinality n with this property, we'll call it n point lambda universally optimal. Now, a reasonable question to ask then is, what relationship does this n point lambda universal optimality have to the more well-known notion of Konin-Kumar of universal optimality, say of a lattice? And okay, here's sort of one direction. So suppose lambda is universally optimal lattice in RD, and we have some sublattice gamma of index m. Maybe it's easier to just think of the sublattice as being the lattice itself of index 1. But so suppose we have a sublattice gamma of index m, and its fundamental domain is given here, it's omega sub gamma. Then if we scale our original lattice lambda by a factor of j and intersect it with this fundamental domain, we're going to get a finite point configuration, and the universal optimality of lambda is going to guarantee that this finite point configuration is universally gamma optimal. So it's universally optimal with respect to the sublattice. And since we know examples of universally optimal lattices, the integer lattice from the original Konin-Kumar paper, and then E8 and the Leach lattice from more recent work of Kohn, Kumar, Miller, Radchenko, and Vyazovska, well, these are going to give us examples of finite point universally optimal configurations with respect to different lattices. Now, I think, I guess this sort of begs the question that A2 is, conjectured to be universally optimal in the plane. And so our starting point would be to show that certain scalings of A2 intersected with fundamental domains of sublattices of A2 give you finite point universally optimal configurations with respect to A2 or its sublattices. And indeed, that's what Doug and I are working on. So we have our lattice A2, the fundamental domain generated by these two column vectors shaded in blue here. And our kernel that we're interested, or that we'll be working with, are these A2 periodizations of the Gaussians, right? Because those characterize all the completely monotone functions of distance squared. And so then our configurations that we hope are universally optimal with respect to A2 are going to be scalings of A2 intersected with this fundamental domain. So for example, if you take A2, scale it down by a factor of 2, and then intersect with this fundamental domain, you're going to get a 2 squared, so a 4-point configuration pictured here. And the claim is that this 4-point configuration is energy minimizing for every kernel, which is a periodization of the Gaussian. So for example, this configuration, should do better in an energy minimization sense than something, a generic 4-point configuration like that. All right. So what's out there in terms of universally optimal endpoint A2 configurations? Well, there's not many rigorous results yet for the n equals 2 and n equals 3 case. So looking for a 2-point or a 3-point configuration in this fundamental cell, which minimizes energy for every periodization of the Gaussian. That's settled by Yujin Su, a former student of Doug's, in 2015. And here, this honeycomb structure gives you a 2-point configuration when you intersect it with the fundamental domain, and a scaling of scaling and rotation of A2 gives you a 3-point universally optimal configuration. But higher than that, everything is open. In particular, the n equals 4 case is open. And I guess I should say, yeah. So okay, we've said that this universal optimality of a finite configuration with respect to a lattice, that's a weaker condition than universal optimality of the lattice. But there's a reverse condition as well. So in 2007, not exactly maybe in these words, but Kohn and Kumar conjectured that every scaling of A2 will give you an n squared point universally optimal configuration with respect to A2. And if that were to hold for every n greater than 1, it would follow that A2 is universally optimal in the plane. So there's this dual relationship. If a lattice is universally optimal, then it gives you finite configurations which are universally optimal with respect to the lattice and its sublattices. On the other hand, if every scaling of a lattice gives you a universally optimal configuration with respect to that lattice, well, that gives you the universal optimality of the lattice. And we've been talking about the optimality of A2 with respect kind of to this notion of Kohn and Kumar, but conjectures about A2 being optimal, these go back a long way. For just one example, Saf and Couillars in 1995, I think conjecture that in some sense that A2 is minimizing energy for all Riesz kernels of sufficiently fast decay. So, all right, we'd like to show, this is sort of what we're after. And okay, for all n greater than 1 is a very ambitious goal, but for n equals 2, maybe that's a little more doable. We'd like to show that A2 over 2 intersected with the fundamental domain is 4-point universally A2 optimal. It seems like that. All right, so that's what we'd like to do. And, how are we going to get there? Upper bounds, right, on this, a reasonable start would be to find upper bounds and lower bounds on this finite energy. Okay, upper bounds are not so difficult. Any 4-point configuration is going to give you an upper bound on the energy just because it's defined as an infimum, but lower bounds are much more difficult. So how are we going to get those? Via the linear programming method. So we'll take lambda to be a full rank lattice. Then our dual lattice of lambda is going to be the set of vectors v, which when you dot them with every vector in lambda, you get an integer. And from this, it follows that these exponentials in terms of dual lattice vectors give you an orthogonal basis for L2 of the canonical fundamental domain. And I guess these we sort of think of as being a Fourier basis and are crucial for obtaining the linear programming bounds. All right, so if we take a function g in L2, let's see if we can get a lower bound on the g energy with a couple more conditions on g required. So g is in L2 of the canonical fundamental domain, then it has this Fourier, what we call a Fourier expansion. And let's assume that its Fourier coefficients, the g hats, are non-negative for all the non-constant coefficients. Well, then, okay, the g energy, it's equal to the Seer negative n times g of 0 plus summing over the lattice g hat of v times these moments. And I guess the move in these linear programming bounds is to note, well, if each of the g hats is non-negative, then summing over the dual, every single vector, or every single term in this sum rather, is going to be non-negative because this is a modulus of a complex number. And okay, this is a non-negative number by fiat, by assumption. So, okay, let's throw away every single one of those terms except for the term corresponding to the 0 vector. Certainly we're going to get something smaller, and that'll be, okay, this term is unchanged. And all that remains is the term corresponding to the 0 vector, but now this modulus is, exactly, or this is exactly n in the interior, and so we get an n squared term. So for any function g, and this was completely independent of the configuration omega n, so the g energy of omega n has to be at least as large as negative n times g of 0 plus n squared times g hat of 0, or the 0th Fourier coefficient. Okay, but what if our function, what if our kernel that we're interested in doesn't have non-negative Fourier coefficients? How are we going to use this bound on the G energy to get a bound on the F energy? Well, the trick is to take, just look for G's which are staying below F, and now any bound on the G energy is also going to give you a corresponding bound on the F energy. So if F stays above G on the entire fundamental domain, then the minimal discrete F energy is larger than the minimal discrete G energy. And by the previous argument, that's got to be at least negative n times G of 0 plus n squared times the 0th Fourier coefficient. So that, looks different, or it's not exactly the bounds we see in every other context, but it's sort of the same type of argument. Now, the question though is, this seems very crass to throw away every single term in the sum except for one. When there's infinitely many terms, probably you're not going to get a very good bound, and you might wonder if you're ever going to get a good bound out of this sort of with this operation. And in fact, you will. Okay, these go back to coding theory results of Delsarte and Levenstein and Yudin, and now more recently. Of course, these are being used by Kohn and Elkes to get Kohn and Kumar and Vyazovska, along with the Kohn, Kumar, Miller, Radchenko, Vyazovska team, to get energy and packing results in Euclidean space. So putting things together here, suppose you've got some G, which is an L2 of omega naught. G stays below F. I guess G has to be pointwise equal to its non-negative Fourier expansion. Maybe I needed that on the last slide as well. Then what can we say about the F energy of a multiset and the G energy of the multiset? Well, exactly what we said on the previous page. The F energy is larger than the G energy, or at least as large, which is larger than or equal to n squared times the 0th Fourier coefficient minus n times G of 0. And when do we get equality throughout this entire string of inequalities? Exactly when first G has to agree with F at every single difference of points. So for all x not equal to y, G and F have to agree at their difference. That will ensure that the G energy and the F energy of omega n are the same. And moreover, to get equality in this second term, we had to have that every single term that we threw away, all but the 0 one, should have been 0. The only way to not decrease a sum when you're throwing away non-negative terms is for all those terms that have been 0. In which case, either for every vector v, the coefficient must be either 0 Fourier coefficient, or this moment, the complex number whose modulus we were looking at, that complex number must have been 0. And if you get equality throughout, if both of these conditions are true, then you've shown omega n is optimal for both F and G. So that's what we're after. Then we're gonna want to find a G which satisfies this, satisfies these first conditions, and then has equality throughout. Now, what's equality throughout going to entail? Well, okay, if you need G to interpolate F at a variety of points, and then okay, and each one of those is going to represent an equality condition on G. So the fewer of those, the better. That's going to give you less. You'll have an easier time finding a G if you only have to agree with F at 1 point or 2 points. And then moreover, you'd like lots of freedom. You'd like lots of Fourier coefficients, which you can toggle to set your G, to set up this interpolation. And so we'd like lots and lots of these moments to vanish. Now, that sort of gives the motivation for why the scalings of A2 are going to be such a, or potentially fruitful for this method, because one, they have sort of a minimal number of equality conditions, and two, lots of the moments will end up vanishing for these scalings of A2. And okay, that's our first result. Not quite a universal optimality result, but for many choices of the Gaussian parameter, so for A small enough, say less than 3, or A very large, greater than 30, or I guess maybe that's not very large when we go all the way out to infinity, then the 4-point configuration, which we showed before, is going to be optimal for every periodization of the Gaussian. And I guess we should add that this gap in the parameters from 3 to 30 is, not that we suspect the result fails there. In fact, we think we have the magic G, the interpolating G, which would prove that it's optimal. This configuration is optimal, but rather some technical difficulties in showing that interpolant stays below our function f, which we'll get to. So we suspect that this should be turned, that this can be turned into a universal optimality result. So, right, okay, this 4-point configuration is optimal for all but a compact region of the parameter. Yeah, is there a question?
Yeah, excuse me. So can you show some local optimality results, for example, that you can show that if you move these points a little bit, then they will not get better?
Well, so for every A except for between 3.5 to 30. Okay. Oh, in that region, we haven't looked into that. I suspect that we couldn't at the moment, and we're relatively hopeful that if we keep pushing, this shouldn't be an insurmountable thing. But I don't think at the moment we have anything like these, like a local minima or anything like that.
Okay, thank you.
I don't know, Doug, is that what would you agree there?
Yeah, I couldn't hear the question, but I agree. I don't think we know that there are local minima there. It's really the stay below is right now is the harder issue for us. But we were hoping to have this completed for this talk, but
yeah.
So we think it, but okay, yeah.
Yeah. Okay, so for the rest of the time, maybe we can talk a little bit about this regime. What does the proof look like in the case where A is small? And I guess I like to think of that as if A is small, then this periodization of the Gaussian is practically constant. And if A is large, at infinity, then the periodization of the Gaussian is like a bump function at the origin. But okay, the small case where let's consider the small case where it's nearly constant. So I guess first we can think a little bit about what we need out of the interpolant and what functions are available for us in building this interpolant. And then we can talk about the function to be interpolated f. What do we know about it? So to sum up, to recall, we need this magic function g, this interpolant, to stay below f on the entire canonical fundamental domain. We need its Fourier coefficients to be non-negative, and we need it to agree with f at all differences of points in the configuration. But because this configuration is very nice, right, it's a scaling of a lattice, having equality at differences of points is equivalent to having equality at the points in the configuration, or the non-zero points. So there's three equality conditions. Now, moreover, this function f, it doesn't, anytime you periodize by a lattice, you're going to be then invariant under lattice translation. But because A2 has all these extra symmetries, it has these symmetries of G2, which I'm using for the symmetries of the regular hexagon, so that order 12 group. Because A2 has those symmetries, F inherits them as well, which means that F, one fundamental domain of A2 is this regular hexagon. And so rather than F, having its behavior determined by the entire canonical, or this entire fundamental domain, F's behavior is determined by its action, or how it maps points just on this 30, 60, 90 triangle. So 1/12 of the area, which we term delta 30. And so if you can produce an interpolant which has these same G2 symmetries, then it too will be determined just by its behavior on delta 30. And so showing that F stays above G, you could restrict to just looking at this smaller region. And moreover, the equality condition would reduce to a single equality condition, just that F in the interpolant equals our kernel at this bottom right point here. So it makes a lot of sense to look for your interpolant among these G2 invariant functions. Okay, it's reasonable to ask then kind of what are your building blocks, right? Your building blocks of A2 invariant functions are, you know, the Fourier basis that we described earlier, but what are your building blocks of functions that then have this added G2 symmetry on L2? And so how do we get those? You know, we take a symmetry or we average out by the group symmetries and get what are called these generalized Chebyshev polynomials. So for a vector V in the dual lattice, we get its generalized Chebyshev polynomial by summing up, you know, the symmetries, averaging over the symmetry operation in the group. And now this resulting function is guaranteed to be G2 invariant. These Chebyshev polynomials, I think, you know, one good way to think of them is like they're analogous to the Gegenbauer polynomials on the sphere. All right, and something that's kind of remarkable about them is as follows. This is in Lee, Sun, and Xu, a paper from 2012, which is that each one of these is a polynomial in the variables of the two most basic generalized Chebyshev polynomials. So the dual lattice of A2 is A2 rotated by 30 degrees. And so it has a shortest vector and a next shortest vector. We'll call them V prime and V star. V prime, so the generalized Chebyshev polynomials corresponding to those two vectors generate all the others. They're all polynomials in these first two, although the polynomials get very complicated and are not a family that we understand very well right now. And one way this can be shown is via recursion, kind of analogous to how the Chebyshev polynomials on the real line are generated out of recursion, out of cosine and the first and the constant function, and you know recursion your way out to get all of them in the same way. We can show that if you start in the lattice and work your way to vectors of higher and higher higher and higher or larger distance from the origin, you can use a recursion based on the shortest vector and the next shortest vector to show they're all polynomials in terms of these most basic generalized Chebyshev polynomials. So these generalized Chebyshev polynomials are going to be the building blocks of our interpolant, this magic G function. And now, which ones are available to us? You know, we only want to use a generalized Chebyshev polynomial if it's not going to break the sharp bound. And so, you know, we can use the generalized Chebyshev polynomial corresponding to a vector V if the corresponding moment, the moment corresponding to the vector V happens to vanish. And for us, in the setting where we've scaled A2 by a factor of 2, lots and lots of vectors or lots and lots of moments vanish. Every single moment or every moment vanishes if the vector V is sort of non-zero mod 2 in the sense that it's a combination of the column vectors, you know, generating A2 star where the weights are non-zero mod 2. In particular, this includes our two most basic ones. And we should say that if we had scaled A2 by a factor of n instead of 2, then the moments vanish for every single dual vector, which is non-zero mod n. So this 2 is an artifact of the fact that we scaled A2 by 2, factor of 2 to get this 4-point configuration. But so in the 4-point case, the important thing to note is that we have available to us the two most basic generalized Chebyshev polynomials, the CC of V prime and the CC of V star. All right. So I guess that's kind of sums up what we have at our disposal to build our interpolant. We have lots of these generalized Chebyshev polynomials. They're invariant with respect to G2, and that makes your equality and your inequality conditions much easier to work with. And the two generalized Chebyshev polynomials that we're going to work with are the two most basic ones. Now, I guess we also need to have some understanding of our function f, you know, the thing to be interpolated. And for that, we need to think a little bit about the one-dimensional theta function. So, excuse me, we'll take it to be defined in this way. as a periodized Gaussian, like what we said before, up to a constant, up to a constant c, this c, being a parameter in the function. And via Poisson summation, we can think of the one-dimensional theta function as also a sum of cosines. So a sum of the Chebyshev polynomials. And we should note that this c parameter, depending on if c is large, then this bottom sum is going to converge rapidly, right? These e to the negative pi k squared c terms are going to converge quickly as k grows large. But if c is very small, then the opposite will happen. This sum up top is going to converge very quickly because, pi over c is going to be a large number, and e to the negative pi over c is going to decay very quickly. And that sort of explains why we're able to get the result currently for a very small and a very large. In one setting, we're working with, in each setting, we're trying to work with the corresponding sum that decays rapidly and get really good estimates on this theta function. And so there's this intermediate region where neither sum is decaying very quickly, and we can't get estimates on this theta function that are accurate enough to show that the interpolant stays below our function. But anyways, one nice property of the one-dimensional theta function is if you think of it as a function of cosine, right? Each of these cosine 2 pi k to the x can be written as a function of cosine 2 pi of x, via the Chebyshev polynomials. And if we think about it as a function of cosine, it becomes absolutely monotone on the interval -1 to 1. And strictly so, where absolutely monotone means that the function and all its derivatives are non-negative, and strictly means, I guess, that they're all strictly positive. So this change of variables in terms of thinking of it as a function of cosine makes the one-dimensional theta function well behaved. And that's important for us because our function to be interpolated, this f again is the periodization of the Gaussian with a parameter a. F decomposes into a sum of tensors of the one-dimensional theta functions. And I guess this is a lot to look at, and the pi over 3a and the pi over a are, I guess it's a lot on the eyes, but the upshot is that this function f decomposes into products of the theta functions, this one involving x2 and x1, and this one involving x2 and x1. And so if you have very strong bounds, if you have very accurate bounds on the theta functions, you can use those to get very accurate bounds on our kernel. And now, as we said before, these theta functions are well understood in terms of, we think of them as a function of cosine. And so if we make that change of variables, mapping each of our coordinates into a cosine, then we can think of our kernel as in these new variables, and therefore in terms of these theta tildes, which is theta tilde being the absolutely monotone version of the one-dimensional theta function, where we think of it as a function of cosine. And that's what we've got here below. So under an appropriate change of variables, this function, our kernel, is a sum of two tensors of absolutely monotone functions. And so that's, we can get a lot of mileage out of that decomposition of our function, of our kernel function. Moreover, this change of variables, which we use to get all the one-dimensional theta functions in terms of cosine so that they're absolutely monotone, that same change of variables is going to make our two most basic generalized Chebyshev polynomials. They're polynomials under this new change of variables, which maybe is surprising. And so, once we've changed to this T1, T2 regime, our interpolation, which was previously interpolating this kernel function periodization of the Gaussian via the generalized Chebyshev polynomials, that turns into a polynomial interpolation problem. And here I've got it set up, or I've got it depicted. So we have to interpolate at exactly 1 point. So the interpolant has to match our kernel at this 1 point p hat. And then we also get other necessary conditions. If you have equality here and f needs to stay above G on this entire shaded region, well, then that gives us inequality conditions on the partial derivatives of F and G, which I've got written below. So all to say, under an appropriate change of variables, the interpolation problem turns into a polynomial interpolation, which in two variables is not easy, but possibly not impossible. So finally, I guess we should say, what is the magic G that we're using? And I've got it here. Right now, it currently only uses, it's just a constant plus a positive term times this most simple generalized Chebyshev polynomial. And we suspect that numerical evidence would agree, I think, that this interpolant stays below F, our kernel, for every choice of the parameter, but right now that's being a little bit fickle. So I guess the last thing I wanted to note is that in the small a regime, again, the difficulty, it's very easy to show that this interpolant has has a positive Fourier coefficient, or that this coefficient is positive, and that it interpolates F at the right point. That's straightforward. So it all comes down to showing that it stays below our kernel. And that's extremely or pretty tight thing to do, because as the coefficient, as the Gaussian parameter goes to 0 and our kernel is effectively constant, right? As if you periodize Gaussians, as the Gaussian parameter gets small, you're effectively looking at the constant function. So for example, let this parameter, the Gaussian parameter, be √3. I'm not sure if this is visible, but basically F, its total variation on the entire region is something like 0.1 or 0.01. But the difference between F and its interpolant is on the order of 10 to the -9th, and that only gets worse. So the total variation is 10 to the -1 of our function, but the difference between it and its interpolant is 10 to the -9th. So there's not very much wiggle room between the interpolant and the function itself. Okay, and so how do we manage to show the interpolant stays below F if there's so little wiggle room? Well, we have very technical bounds on the theta functions, the one-dimensional theta function, using this Jacobi triple product representation. And as this parameter C gets small, this product is going to converge very rapidly. And so with only a few terms, you can get really accurate representations of the theta function. And it turns out that those are going to be good enough to show that the interpolant stays below our function. Last, I want to mention, so at the beginning of the talk, we mentioned how universally optimal lattices would give you periodically, or configurations that are universally optimal with respect to the lattice, but also with respect to all of its sublattices. And so that's another thing we've looked into, is not just looking at configurations with respect to A2, but configurations with respect to sublattices of A2. One nice sublattice is the sublattice Z cross √3 of Z, and this rectangular sublattice. And so we have two results in this direction. First, we have a 2-point configuration, which is universally optimal with respect to this rectangular sublattice. That's maybe just an observation that's pretty quick to get. And then similar to the 4-point result, we have a partial result about an optimal 6-point configuration, which is optimal for all Gaussians where the parameter is sufficiently small. The Gaussian parameter is sufficiently small. And here we have pictured the 6 points, which give us this optimal configuration. What did I want to say here? Oh yeah, just as in the previous case where our example, you have these generalized polynomials which mod out by the symmetries of the lattice, and then under an appropriate change of variables, you obtain a bivariate polynomial interpolation problem. The same thing is going on here, where we obtain a bivariate polynomial interpolation problem. And so moving forward, that's kind of one of the big cruxes of the project, is better understanding these bivariate interpolation schemes so that we can show that our interpolants stay below the kernels. So I guess I'll stop there. And if there are any questions, I'd be happy to answer them. Thanks for your time and attention.